Professor Capaz got his bachelor's at PUC Rio de Janeiro in 1989. He got his master's there too in 1991. And then he went to the United States, to MIT, and got his PhD there in 1996. He did two postdocs or three postdocs, one at UFRJ at the Federal University of Rio de Janeiro in 1996 and 97, and at UC Berkeley in twice, 2003 to 2005 and 2009 to 2011. And since 1997, he's a professor at Federal University of Rio de Janeiro. And he has recently, in 2021, been appointed the director of LNNano. And he's going to talk to us about that today. And the title of his talk is Breaking Ultrathin Ionic Wires at LNNano. So, Professor Capaz, thank you very much for talking to us. And the microphone is yours.
Thank you, George. Thank you very much for the invitation. It's really nice to participate in this webinar series. Would be even nicer if I would have the opportunity to visit you guys again in Uberlândia, but maybe next time we will be able to do that. So I divided this seminar in two parts. The first part, I will briefly describe the LNNano, the Brazilian National Nanotechnology National Lab. As George said, this is where I'm holding this position of director right now. I think this is, first part is like an advertisement of the facilities we have here, which are multi-user and open access facilities. I think it's important to broadcast as an opportunity to, mostly to experimentalists all around Brazil, that we have these facilities that people can come and use in the field of nanotechnology. And in the second part, I will describe some recent work we did in collaboration with experimentalists here at LNNano and on breaking monatomic wires of zirconium oxide. Okay, so let's then go ahead to the first part. So the LNNano is part of CNPEN, which is a larger structure. It's the Brazilian Center for Research in Energy and Materials. And this center is composed of 4 different national laboratories. Of course, the most well-known structure is the Sirius. It's part of the LNLS, the Brazilian Synchrotron Light National Lab. But also in the same campus in the city of Campinas, we have LNNano, which has these 2 buildings. Once again, this is mostly for non-Brazilians, but I mean, we are located here at the city of Campinas. The 4 different national laboratories is LNLS, Brazilian Synchrotron Light, Synchrotron, there's an R missing, Light National Lab. We have the LNBR, the Brazilian Biorenewables National Lab, LNBio, or Bio, it's Brazilian Biosciences National Lab, and finally us here at LNNano. This is a really nice and unique R&D ecosystem we have here, and we try to act in a coordinated way within those 4 different national labs. First of all, by providing facilities, as I said, open user facilities for people all over Brazil and from abroad. And also we do our own internal research activities in 5 different programs: health, renewable energy, renewable materials, agro-environmental, and quantum technologies. So I'll briefly describe those activities in the next few slides. Of course, I need to mention that the Sirius is our, as I said, our most well-known facility. I'm not a synchrotron light expert, but I mean, these are the Sirius main parameters. I'm not going to go in detail too much about that, but I just wanted to point it out. Something that I consider very important is that Sirius is roughly 85% made in Brazil. Actually, this is a kind of philosophy that LNLS has followed since the first synchrotron light source, the UVX, and also in the Sirius project, this is also true. For Sirius, the commissioning timeline, of course, was slightly delayed because of the pandemic, but the first beam line opened in December 19, and nowadays we have 6 different beam lines already accepting proposals for commissioning experiments. So you can, if you want to use Sirius, you have this, as I said, 6 different beam lines, Manacá for macromolecule crystallography, Caterete for X-ray coherent diffracting imaging, Carnaúba for X-ray spectral nanoscopy and nanodiffraction, EMA for samples under extreme conditions, Imbuya for nano and micro Fourier transform infrared spectroscopy, and IP for soft X-ray inelastic scattering and photoemission. And also these support laboratories are also opened already as well. So the mission of CNPen and of course LNNano also share this we call axis of activity. There are 4 different, let's say, dimensions in our mission. First is that, as I said, to act as an open facility for people all over Brazil and abroad, to do our in-house research, to be support for innovation, interaction with the private sector and industries in Brazil, and also to provide education and dissemination in the form of, workshops and courses, and more recently we opened CNPen opened his own undergraduate course on science. It's called ILUM. I'm not going to talk too much about that, but if you want information about that, you can also find it online. So it's also part of our activities in education and dissemination of knowledge. So let's go closer now and talk about LNNano. LNNano was created in 2011. So it recently had its 10-year birthday. And since then, it had more than 6,000 external users. Roughly, you have about 600 users per year. It is part of a larger system or a larger ecosystem of nanotechnology laboratories called CISNano, a National System of Laboratories on Nanotechnologies. LNNano is one of the strategic labs of CISNano. So the other labs are described here in this map. It's probably the largest fully dedicated to nanotechnology lab in the country. So, but our team is not very large. We have actually 15. This is has to be updated. We have actually now 16 researchers. These are our researchers. And also, we have what we call specialists, 15 specialists. These are people with PhD and also with postdocs. But differently from the researchers, they actually work in a more devoted way to the facilities and to work on providing the external users to external users the best use of those facilities. And also we have 20 technicians and 3 administrative support. So we divide ourselves in 3 different divisions. We have nanomaterials division, nanobiotechnology division, and devices division. As I said, we roughly give we have around 600 external users per year, and roughly, I don't know, 500, 400 research proposals every year. Regarding our internal research, we have, as I mentioned before, 5 different R&D programs of, as I said, not exclusive for LNNano, but also for all CNPen internal research of the 4 different national labs. And besides that, we also have research activities in what we call transversal enabling technologies: electron microscopy, cryomicroscopy, micro and nano fabrication, and theory and data science. So now I will describe our 3 divisions. Basically, I know this is probably not very, fun, but I'm just going to show, run through all the equipment, some of the most important equipments that we have. Again, this is just to advertise and to stress that once again that they are available for external users. Starting with our nanomaterials division, it holds the largest microscopy facility in Latin America. So we have TEM, Titan Themis microscope. These are some examples of results using our microscopy facilities. This one I'm going to describe in more detail in the second part of my talk, is the breaking of zirconia monatomic wires. So I think this was supposed to be a movie as well. It's not working. These are different examples on the study of glass formation and the tomography of gold nanocages. And these are some examples of recent publications in electron microscopy enabling technology. Okay. We also have scanning electron microscopy, SEM, and dual beam facility. Our AFM facilities, we have 4 different AFMs with a wide variety of techniques that can be used in different systems, and wet systems and dry systems. We have our scattering and spectroscopy lab with X-ray diffraction, XPS, Raman. Our synthesis facility, this is our nanomaterial synthesis facility, mostly inorganic nanoparticles of different types. We have our photoelectrochemistry facility. This is very much related to the research activity we have on hydrogen production using both electrolysis and photoelectrolysis, and also related to our hydrogen production program. We have this nanoceramics processing laboratory. And as I said, this is related to our renewable energy program. We have a sub-program on green hydrogen production. The idea is to, again, produce hydrogen using non-pollution, green methods. And typically this is done by doing water electrolysis or photoelectrolysis. And we have very strong activity on this area. And these are some examples of recent publication on this field. This is mostly focused on nanomaterials development for electrodes and photoelectrodes for water splitting applications. All right, now going now to our devices division. We have our nanofabrication facility with over 200 square meter clean room area, in which we have an e-beam lithography facility. This is our clean room, our Wraith e-beam equipment. We also have a microfabrication lab, and also it has a very strong activity on microfluidics. And also within our devices division, we have our thin films and electron measurements facilities, in which we have a MBE. It's originally a 3.5 MBE chamber that was recently adapted to grow 2D materials of the group 5 elements, like arsenine, for instance. This is where we're developing trying to produce 2D arsenine films. And also we have a PPMS with the possibility of making electrical measurements at very low temperatures and very high magnetic fields for device characterization and studies of nanoelectronic properties. All right, so this is once again some results from our recent results from our micro and nano fabrication facilities, and some recent results from this division. Okay. We also have a very strong activities on sensors and biosensors used in diagnosis in our health program and biomonitoring. So, and these are some selected recent results on different types of sensors, mostly electrochemical sensors for in biological fluids, and those are produced here at LNNano. Finally, we have our nanobiotechnology division. This nanobiotechnology division has, again, a set of laboratories. One of them is the nanotoxicology and nanosafety facility, in which, both for academic but also for industries, people can come and analyze the toxicology impact of nanoparticles or nanomaterials. And we have a very unique facility and well-known in Brazil facility for that purpose. We also have the only cryo microscope, electron microscope facility in Latin America, with two different microscopes. Cryo-EM has a very interesting principle. It makes analysis of biomolecules, and the idea is that you have those biomolecules floating on water in solution, and you freeze this solution very suddenly. So you create amorphous ice, so that provides you with the contrast to see only your biomolecule. And these are some examples of that. Our recent papers on the use of cryo-EM to map the Mayaro virus at 4.4 angstrom resolution, and also the atomic model for human septin eczema. These are two examples of the research done in our cryo-EM facility. Also, the nanobiotechnology division holds research activities on bio and renewable nanomaterials. We have our nanocomposite processing lab, and also renewable nanomaterials lab. We do a lot of research in biomass, and we are particularly interested in the interactions of cellulose and lignin, and different studies of cellulose to provide understanding of cellulose interactions, and also to provide new products, green products based on biomass. So these are highlights of the renewable materials lab. Again, we do a lot of study on nanocellulose, lignin-cellulose interaction, and biomass-based materials and devices. These are some of our recent publications on that field. And also, within the nanobiotechnology division, we have the Nano Environmental Lab. And this is part of the agri-environmental program of CNPEM. We do a lot of research on nanomaterials for environmental remediation and sensing. And also, as I said before, the study of toxicity and nanosafety for nanomaterials. Once again, these are some highlights of our recent research. Finally, I think this is the last R&D program that we actually starting now, the quantum technologies. Nowadays, it's mostly quantum materials and quantum devices. In the future, we are trying to position ourselves as CNPEM as a key player on future quantum technology devices. But at this point, we are doing mostly theory of quantum materials, and these are mostly results from the group of Adalberto Fazio, who was the former director at CNPEM, at LNNano, and now he's the director of the Elon School. These are some results on different topological properties of low-dimensional materials. And this is very much related to the transverse program on theory and data science, in which you have knowledge and capabilities on electronic structure calculations using DFT, machine learning techniques, molecular dynamics simulations, and electronic transport. Okay? And these are further recent work on this area. All right, I think this is, I know this is very quick and very superficial, but the idea was really to give you some flavor of things that the facilities that we have, and emphasize once again that we are fully open for external users and also for collaborations. We are actually hiring. We may be able to see in different, bulletins, SBF, that we are opening a lot of positions at CNPEM, and in particular at LNNano. And we are hiring both experimentalists and theorists. And if you have some interest on those available open positions, please get in touch and we can talk about it. Okay? All right. So now let me move on to science, and let me describe to you recent work we did in collaboration with our experimental friends here at LNNano on the desintering and breaking of ionic nanoparticles. This is a collaboration with Adalberto Fazio. From the theory side, Adalberto Fazio, Bruno Focaccio, and Gabriel Schroeder. And from the experimental side, mostly from our TEM experts, Jefferson, Edson Leite, João Souza, and on synthesis, and Murilo and Tana. Okay? So the question is, why studying desintering and wire formation? I will explain in a minute what I mean by desintering. But the idea is that this is within the general area of studying the thermal stability of nanoparticles under stress. So when we think about thermal stability of nanoparticles, immediately you think about the process of sintering, that is to these different nanoparticles under some thermal treatment, they can sinter, they can become larger and larger, or if you apply some external stress, tensile stress, you can do the opposite process of this sintering, that bringing those let's say, a pair of nanoparticles apart until you break them, okay? And that's the general idea of this study. This is also important because in this way, as we're going to see, we will explore the limits of high-resolution TEM, including analysis of in situ atomic dynamics. So it's very, important as a proof of concept to take this experiments to the state of art of visualization of atomic dynamics. And from that, you usually be able to see new physics and new phenomena. Of course, this is very common in the area of nanoscience and nanotechnology. Everybody remembers the first demonstrations of atomic control and positioning. This is an STM image of from the IBM group. And also here, right here in this lab in the early 2000s, everyone may remember that the experiments by Daniel Ugarte and collaborators in the formation and breaking of gold metallic wires, which was a very, was a huge success at that time. And also, Alberto Fazos from the early days was one of the, and also José Roque, who was our general director of CNPEM, were very instrumental in doing the theory support for those kind of experiments. So we have a long history of, let's say, playing with monatomic wires, and we want to extend this history to another class of wires, to ionic wires. So the idea is that, again, is it possible to create monatomic ionic wires? Well, as I mentioned, in the early 2000s, people already did metallic wires, since it's gold and or the 5D elements. Is an example from metallic wires, but people were also able to create covalent wires, such as the carbon chains. And one of the best ways to stabilize carbon chains is within carbon nanotubes, but people are nowadays able to form and to measure very long carbon chains up to 6,000 atoms inside carbon nanotubes. So we can make metallic wires, we can make covalent wires. The question is it possible to make ionic wires? So this is the question we want to respond. It's not so simple, let me say, because typically ionicity comes together with brittleness. So, in general, ionic compounds are very brittle, so they break very easily. This is a cartoon trying to explain why this is so. If you make some atomic rearrangement in an ionic crystal, it's very likely that it's important that you maintain, for stability of ionic crystals, it's important that you maintain, that you keep global and local charge balance. This is very important to stability. If you locally break charge balance, you have very strong repelling forces that leads the system to crack. So again, this is a cartoon, but if I want to say in words what this cartoon means, this is what I would say. So atomic wire formation requires a very complex sequence of atomic rearrangements, and this is very hard to be compatible with the fact that ionic materials require charge balance at global and local levels. So it would be very hard to envision a sequence of atomic rearrangements that in the end leads to the formation of a ionic wire. In general, you expect that materials that form wires are not brittle, right? So let's see what happens if one tries to do that. Okay. The first part is to produce zirconia nanoparticles. We have a sequence of steps that, of course, myself as a theorist, I have very limited knowledge about it, but I may be able to just explain the very basics. We form some zirconia nanoparticles in solution, and you actually encapsulate these zirconia nanoparticles with some organic compounds. These are oleic acid in our case, and you take this to the microscope grid, right? And when you do that, under the electron beam shower of the microscope, you remove this organic surrounding material, and in the end, you form a very thin layer, one or two monolayers of zirconium dioxide nanoparticles, and they are thin enough that you can visualize those at the TEM, right? So these are snapshots in the evolution of thermal treatment of these nanoparticles. So I think this is actually room temperature, but what happens in general is that these nanoparticles will sinter. I mean, they will grow larger structures. This is what basically it's more favorable from the thermodynamic point of view to sinter those nanoparticles, but locally, in some specific positions, you will see that some regions actually shrink, and eventually they form a pair of nanoparticles that are actually just joined together by a very thin neck. And this happens because of the surrounding strain fields that eventually lead in this particular position to let's say to a tensile strain in this position that eventually leads to what we call the desintering or breaking of the two nanoparticles. Okay. So that's the key idea. The tensile stress promotes local desintering instead of sintering. And so if you try to understand from a macroscopic, from a thermodynamic point of view, what is called the classical theory of desintering, it's very similar in a way to the so-called plateau Rayleigh instability in liquids. So if you think about if you take a fluid stream, this is well known that at some point your stream breaks into droplets, and this is a result from the minimization of surface energy, which is in a liquid is essentially minimization of surface area, right? At some point, it's more favorable from a surface energy point of view to break, let's say, a cylindrical stream of fluid into a smaller droplets. And this is the basic idea behind the classical theory of desintering. So imagine now that you have two nanoparticles or two particles of material, and you either by removing mass from the region or by moving these two walls apart, that is providing tensile stress, you start to shrink this interface between these two nanoparticles. One important quantity to use as a parameter to analyze this process is the so-called dihedral angle. And you see that this dihedral angle starts to decrease until at some point there is an instability. And this instability is very similar in nature to the, as I said, to the plateau Rayleigh instability. So at some point in a critical behavior, it's more favorable to suddenly break those two nanoparticles apart and to form separated structure, breaking the two particles. Okay, this is the classical theory of desintering. So what we want to see from both from experimental and from a theoretical point of view is that can we see this process, follow this process from an atomic resolution, this process occurs exactly like that in atomic resolution. In the time domain, can you see the dynamics of this sintering, of the nanoparticle breaking? So these are the key questions that motivated us to study this phenomenon. So basic question is, as usual, what happens at the nanoscale? So let's see what happens at the nanoscale. This is our, again, with higher resolution, our movie of breaking these two zirconium nanowires, these two zirconium nanoparticles. The black dots that you see here are zirconium atoms. You cannot see, you don't have resolution to see the oxygen atoms. And this, you can see something that is very intriguing and important. This is very different from the classical description. First of all, you don't see any instability. You see that the sintering process goes through until the very end, until you see that here that you form a monatomic zirconium oxide wire, as you can see right now. The second thing, which is important, this dihedral angle, let me run the movie again. The dihedral angle is roughly constant. You can see here. Mentally, you can imagine how this dihedral angle here, you can visualize it, and it remains roughly constant throughout the whole process. That's a very key point. And the reason for that is basically because nanoparticles are very different objects in comparison to macroscopic bodies. Nanoparticles, then, they tend to keep well-defined surface orientations, and this is what you see here. This is because very specific surface orientations have low surface energy, and the idea is that the process happens in such a way that you are moving those two nanoparticles apart, but you always, the system always tries to keep the same surface orientation throughout the process, okay? And these are the take-home message. There's no instability at all at the nanoscale. So this is very different from the classical description. And also the dihedral angle is roughly constant throughout the process. So let us analyze in a more quantitative way these two facts. This is a plot of the width of the what we call the bridge, the interface between the two nanoparticles as a function of time. So it's roughly linear. There's no instability. And this is a plot of the dihedral angle as a function of time. It's roughly constant, right? So, okay, so these are the experimental data. And our experimentalist friends came to us and, well, what's going on? How can we explain that from a thermodynamic point of view? So these two cartoons, actually, they compare the classical description of the sintering that I have shown you before and the new nanoscale theory of the sintering that we are proposing. And the basic difference between those are, again, the constraint of keeping a constant dihedral angle. If you think about this, is a very strong geometrical constraint. And the only way to move these two nanoparticles apart and in the process by keeping this dihedral angle constant is actually to invert the flux of material, the mass flux. You actually need to move atoms to this region and in order to make this thinner and thinner until it becomes an atomic wire. That's the idea. So this was very strange to our experimental friends. And when we discussed that idea with them, they actually did not believe it too much. So, but they can basically go back to the microscope and see what's going on. We can actually determine if atoms are moving to the bridge or from the bridge as the sintering process happens. And this is the result. Actually, theory is right as usual, right? So atoms are actually moving through the bridge. You can mark a very well-defined atomic plane in blue here, and you can follow blue, and one in blue and the other one in yellow, and you can follow how many atomic planes are. You can count how many atomic planes are within the bridge as you move the two nanoparticles apart, and you reach the conclusion that in fact you are adding more and more atomic planes so that you can keep this dihedral angle constant until the system breaks. So these are the take-home message. There's no Rayleigh type instability. The dihedral angle remains constant, as I said, and the mass flux is reversed. We developed a very, simple thermodynamic model for that. I don't think I have too much time to go through that, but we can explain basically those results in terms of energy balance. I will skip that for a minute. If people are interested, I can go back to this by the end of the talk. Okay, so we also went ahead and tried to understand the very final stages of the sintering, which is, as I said, the formation of an ultra-thin ionic wire. So if you go to the very last stages of breaking those two nanoparticles, you have a very complex atomic rearrangements that at some point, initially there is a 3.8 angstrom distance between two zirconium atoms. This is very much compatible with a model of a stoichiometric model of infinite ZrO2 ionic wire under tensile stress. But at some point, there's some atomic rearrangement so that this distance suddenly increases to 4.2 angstrom and 4.3 angstroms. This is impossible for a stoichiometric wire. If you try to extend this wire and eventually breaks, it breaks much before reaching this distance of 4.3 angstroms between two nearby neighboring zirconium atoms. So the only way this is compatible with theory, and these are DFT calculations, is that you have to conjecture that there's a formation of an oxygen vacancy in this process. So if there is an oxygen missing here, then you can then go to larger distances at even 4.5, 4.6 angstroms. Okay, so these are results of quasi-static pooling simulations using DFT that point out that there is a formation of oxygen vacancies leading to the process of a monatomic formation in this system. So what about dynamical effects? How is this vacancy formation? Is it spontaneous? So the vacancy was already there, or what does it come from? To answer those questions, we did molecular dynamics simulations based on DFT. Those are ab initio molecular dynamics simulations. We start with a very thin bridge, and you're pulling those two walls apart, and you can see that the atoms are moving, and eventually there's very complex atomic rearrangements and the formation of an oxygen vacancy. You see there's now the bridge between two zirconium atoms and one single oxygen. Now the vacancy moves to this point, and you see already here the non-stoichiometric piece of wire forming until it breaks. So it always goes through this vacancy formation before breaking. And the vacancy formation is the one leading, the process leading to larger zirconium distances. So the experiments are quite well reproduced by theory. All right. So there's an analogy that we can make between the process of vacancy formation in these systems and the phase transition in a bulk material that under pressure. So let me take a step back. The question we want to answer now is that the process of vacancy formation, does it happen at constant length or at constant stress? So that's the question we want to ask. So let me, again, go back and remind you our knowledge from 3D solids. So if I want to analyze pressure-induced phase transitions in a bulk material such as silicon, so these are total energy as a function of volume for silicon in the diamond structure. And this is a similar curve, total energy as a function of volume for silicon in a different structure, like a beta-tin structure. So the question I ask is at which pressure there is a transition between those two structures. So the way to do these calculations is to draw this, what we call the common tangent. This is the common tangent procedure. And the slope of this line is the energy divided by volume. So the slope of this line gives you a pressure, and that's the pressure that will lead the system from diamond structure to the beta-tin structure. So at a certain pressure, there is a discontinuity in volume. The system jumps from here to there, right? And this is how phase transitions in solids take place. This procedure is equivalent to minimizing the enthalpy. So we can easily show that this is common tangent construction is equivalent to see which structure has not the lowest energy, but the lowest enthalpy, okay? So let's see how those concepts can be used in our case. So the question we want to ask is that is spontaneous vacancy formation under stress? So, I mean, to create a vacancy, it costs a lot of energy, like 6 electron volts, something like that, okay? So the idea is how stress can act in such a way so that the vacancy formation becomes spontaneous, okay? And we have two ways to analyze this process, either at constant length, as I said, or constant force. This is analogous to the 3D case, constant volume or constant pressure. And we also can analyze this using total energy calculations in two different oxygen chemical potential conditions, oxygen rich or oxygen poor conditions. So the idea is that when you form a vacancy, you have to remove an oxygen atoms. And the way to keep the balance of total energy of this process, you have to take this oxygen atom to a reservoir of oxygens. And this reservoir must be described by a certain chemical potential. And there's a range of possible chemical potentials leading to these two extreme conditions, oxygen rich and oxygen poor. This is slightly technical, but if you want, I can come back to this point. But the idea is that we did this 4 different processes. We consider both oxygen rich and oxygen poor conditions, and we considered the process happens at different constraints, either constant length or constant force. So, and the only quantity that we had available to us to compare to experiments is the discontinuity in bond length, in bond distance between 2 zirconium atoms as the vacancy is formed. So as the vacancy is formed, the distance between 2 zirconium atoms jumps experimentally from 3.8 to 4.2 angstroms, and we can calculate the same quantity theoretically using these 4 different conditions. And just by comparing this number, we conclude that likely this process this is the closest match, okay, to this experimental results. So likely the process of spontaneous vacancy formation is happening at oxygen-rich conditions and with a constraint of pulling the two wires at constant length, at different steps of constant length. So the system equilibrates at a certain length, and then you move the two walls apart again and let the system equilibrate, and so on and so forth. Okay, so this is a final conclusion of this theoretical analysis. From this comparison, we conclude this rupture occurs at constant length condition and oxygen-rich conditions. So I think I'm now at the end of my talk. Again, I thank you very much for your attention, for listening, and I'm available and open for questions. Thank you very much.
Thank you very much, Rodrigo, for this very, very nice talk, and we are open for questions. I understand that Edson had problems with his connection, so I don't know if he's going to be available for questions. Anyone raising his or her hand? I have a pair of questions. I will go from the beginning on your part describing the LNNano. You mentioned the clean rooms. I know that clean rooms are very expensive and they are ranked according to how clean they are. They have a ranking system. How do the clean rooms at LNNano are ranked regarding this?
Yeah, so this is, there are different notations. I'm not an expert. This is ISO 5, ISO 6, ISO 7. I think it's more common notations is class 100, class 1000, class 10,000. So we have the cleanest room or the cleanest region within a room that we have is a class 100 room. So I hope this means something to you, but it's very experts in the field know what that means. So it's a very clean room, but it's very compatible with the other nanofabrication facilities outside Brazil. But it's, I mean, abroad in the US, you have much larger facilities compared to ours. But the cleanest room we have is a class 100 room.
Oh, okay. There was a break in your connection for a while. The other question I have, let me see if anyone raised his or her hand. No, apparently not.
Fine.
Who is that? Peter?
Yeah, I raised my hand.
Okay, yeah, I can see that something happened here. Yeah, go ahead, please.
Rodrigo, thank you for your nice talk. But looking at this actually old metallic wires, and then you showed I didn't know about the covalent wires that you said are up to 6,000 long, right?
Yes, yeah. Now, encapsulated in carbon nanotubes, they can synthesize as long as 6,000 carbon atom wire.
And those metallic, I see there are half a dozen of atoms long. No? How about these ionic wires?
Yeah,
are they stable? How long can you, in principle, grow those ionic wires? Have you any idea already?
Yeah, that's a very good question. Our wires are not so long. So it's just let me go back here. In the very final stages, you have basically 2 or 3 zirconium atoms with some oxygen atoms between them. And so these are not very long wires. They are not very stable. I mean, long wires are apparently not very stable, but they are long-lived in terms of the time scale. This is a time scale of seconds or milliseconds, which is huge time scale compared to atomic movements, right? To the typical frequency or period of atomic vibrations. This is a very long time. So, but as soon as you move the two particles apart slightly further away from each other, then the wire breaks. So the wires are not very long, but they are stable in the time scale of atomic movements.
Okay, thank you.
I have, if there is no other question now, I have another question. You mentioned that you guys are trying to grow 2D arsenic. Has this been grown anywhere else in the world?
Yes. I don't know, again, the details, but yeah, there are some results of 2D arsenic, yes.
Okay.
But yes, I don't know the details. And also, I think other group 5 elements as well, like phosphorines, I think is the most well-known. But arsenine, also people who were able to grow that already. Okay.
Zirconium oxide is an insulator, right?
Zirconium oxide is an insulator. Yeah, that's right.
In the bulk, but what do the DFT calculations say about the nanowires? They keep being.
That's a good question. We actually did not explore electronic properties.
Okay.
And that's an excellent suggestion of a future work. In the old days of metallic gold nanowires, this was a very nice experiment because also besides the structural information, the Ugarte group was able to measure conductance, right, through these very, very thin wires. We cannot do this because you have to couple to a reservoir, a metallic lead, right? Which it's very easy to do that in gold, but in our case, it's very hard to do because, as you said, the bulk zirconia is an insulator. So the reason, of course, we can do calculations and see if it's a metal or semiconductor, but we are not very much. It's very hard to measure that experimentally. So that's probably the reason we didn't do that. But it's an interesting suggestion.
So it's not connected. So go ahead.
I couldn't hear you.
I said that I am not sure I can see the raised hands because I am not the host. So if anyone wants to ask a question, maybe it's better to open the microphone and ask the question, or write it on the chat. I have another question. I think it's the last one. Can you test the conclusion of your theoretical work by changing the environment? Like you got to the conclusion that it's an oxygen-rich situation, right? Can you change the environment and see if the results change?
That's an excellent question. I have to ask that question to our experimental friends, but I would assume this is very hard to do. This is a question that actually, anytime we do calculations on defects such as this, and we make reference to this different oxygen different reservoir conditions, people ask the same question. So is it possible to make experiments with varying, the oxygen rich, in this case, and oxygen poor conditions? I would say this is very hard. In principle, one would have to think about the possibility of doing experiments in different pressures of oxygen pressures within the chamber. But I assume, I have the impression that this is very hard to control.
Okay. Let me see if there is Any other questions? Edson is always the one who asks a lot of questions, but he is having trouble. He's having trouble connecting. We didn't ask you that because Edson broke his connection. He always asks that if you mind that we record your talk. We recorded it anyway, but we ask the permission to post it in our YouTube channel.
No problem. Yes.
No problem. I'm gonna be sending you an email between today and tomorrow asking for the slides too that we post together with the video in our YouTube channel. So I will be sending you an email. Let me see.
Hey, Jordi.
Oh, Edson. Yeah, Edson.
Actually, I'm struggling with my connection here. I missed a great part of your talk, but it was great to see.
No worries, Edson. It's going to be in the YouTube.
Actually, I meant to click on the button at the beginning of the talk just to start recording. So apparently the system is smart enough. So even if my connection is break apart, it keeps recording. So
great.
Good. Okay, sorry for this problem here on my side.
Okay, so I assume that you don't.
Thank you, Rodrigo.
I assume that you don't have a question, Edson, because you didn't manage to watch the seminar.
Yeah, it was pretty bad. Yeah.
Okay. Okay, so Rodrigo, thank you very much again for this very nice talk and for accepting talking to us. I hope you can come back next year and talk about new developments, and you are invited already.
Excellent. Thank you again very much for the invitation, and it was very nice talking to you, and hopefully we'll see each other soon in Uberlândia. Thank you.